Sir, thank you for the introduction. I'm Major Jarrod Robinson. So you just heard what I was going to say on the first slide, so we'll just start now. So why did we do this study? So that leads us into our motivation. The current armor system is a monolithic ceramic plate. It's susceptible to cracking due to shock of dropping, mishandling, storing it improperly. Even one impact by armor-piercing round, as you see up there on the top right, it causes massive fractures throughout the plate. Army testing requires that when you're using an armor-piercing test that impacts are no closer than 6 inches apart for a multi-hit system. So our effort was to look at different combinations of materials, polyareas, ceramic spheres, to build a plate that's, one thing that we wanted to look at was neutral buoyancy. The other was flexibility, and then multi-hit. If you look at the bottom right, that small circle indicates just the damage area, so you could get hit within an inch of that one impact and still have protection. So that's a vast improvement over the current system. So three questions dominated the research. How does our ceramic spheres, and as far as energy absorption, how do they perform as to a monolithic plate system? We compare and contrast. This is a pure experimental thesis. And then how do the ballistic encapsulation, how does that perform in penetration performance? And then how does the chemistry, the blend of different sizes, different purities of alumina, and then also we compare to a silicon carbide. So there's different chemistries involved, and I'll show those. So the research effort, within the study, we use a ball bearing, a chromium steel ball bearing of 3/8 size as the penetrator, and that's really inexpensive to repeat the shots. We get about 100 per bag, or about $10 a bag. What this allows us to do is we can track the back end of that projectile through the front face interaction. This allows us to get the position, the velocity, and the acceleration, which allows us per time step to calculate the work. What you see here is a image captured by the Shimatsu camera, incident on a silicon carbide plate. It's 0.635 centimeters thick. Frame rate's 10 million frames a second. Two things to notice: the spark on impact and then the debris field. Both these interactions impact our ability to track past 8.2 microseconds on all our targets that we fired. So that's the baseline, is 8.2 microseconds of viewing of the interaction. There's more that happens. Total time is around 150 microseconds of impact. We only capture 8.2 microseconds of that. But what you get here is a good understanding of what's happening in dwell in the first few microseconds. So how do we track these things? We track them through TEMA, which is track eye motion analysis. The first image on the top left gives us a correlation. Points 1 and 2 are a known distance, the diameter of the chrome steel sphere. Point 3 is the desired tracking point, and that's where we focus our tracker. That's a zoomed in portion on the far right. That provides you a correlation of the pixels inside that box is what we're going to track through the entire time steps. The bottom graph gives you a depiction on a multi-axis of position, velocity, and deceleration. And we calculated the work using TEMA in the first 8.2 microseconds, getting the position, the velocity, and deceleration to output in a timetable. That timetable, we know that each time step is 100 nanoseconds, and we're able to back out the work that way and find the instantaneous force per each time step, and then sum those up over 8.2 microseconds. Now we want to validate that method. So we use a method by which to get an energy difference. So we picked two targets to do this for: a silicon carbide plate and then an open spheres, like this. And what we did, and I'm going to pass these samples around now. These are just samples of what you saw on the first slide. They're different encapsulations. And this is going to provide reference later on. And this is ultra-high molecular weight polyethylene. That's what we used on the backing for the actual ballistic testing. So when we compared TEMA versus the energy difference is a simple energy difference formula. But what this did is we knew the chrome steel sphere's sound speed, 5,800 meters per second. So what we did is we found where the first indication of deceleration, and we backed up. We did a simple calculation and found the initial velocity that way when it impacted. And that literally correlated to when we saw the spark. And so, okay, all right, that makes sense. So we grabbed that value for initial velocity. Then we notice on the chart here where the green slope becomes constant. We choose that to be our final velocity. We do a simple energy difference calculation, and then we realize that we're within 3.5% of what we're calculating in TEMA using a LabVIEW program. So they're in agreement. And so we move on utilizing the TEMA approach. Here's our ballistic testing. All our ballistic testing was done over at the golf course at Monterey Pines at the gun lab. We have Dr. Gamache has many guns over there, but I use the light gas gun, a 1-inch light gas gun, the high-speed camera, and various tools to hold the targets in place. The key thing here is the shots were very inexpensive to do. He makes his own nitrogen with a nitrogen generator. We also print our targets. We 3D print our targets here on campus, cutting the cost down, because one of those sabots, if you were going out in town and purchased, are around $20 each. So we're able to shoot the gun for like $5 each shot. So we noticed that there's an energy variance. And so we wanted to explain this via a simple elastic model. So we took the two extreme cases and looked at those, a 7-sphere impact and a 3-sphere impact, impacting in the interstitial or impacting directly on one of the spheres. That's what those indicate. There's an 18%, at the worst case scenario, there's an 18% difference in energy loss. And we're going to go back to this, and I'll call this back, but understand that this is just the simplest case of an elastic model. Notice that our case is an inelastic collision, and there'll be a little bit less. So our test matrix consisted of 60 shots in total, encapsulated and non-encapsulated. We did aluminum, we did K5 and HFM27, those are going around. Here's the work performed versus incident velocity. We did shots from 5,000 PSI down to 1,000 PSI for each target set. So 5 shots per target. What that allowed us to do is to have a linear relationship or exponential relationship in the data. That allowed us to create an equation that we could plug in our desired incident velocity of 500, 600, and 700 to baseline all the different data on all the models that way, and we could pull out the work done at 500, 600, and 700 meters per second. And that provided us an ability to compare all the different encapsulation that way. Oh, one last thing here. All this was a standard deviation of about 20%. And that's that variation that we found. And I point back to that elastic model that provides insight into the variation in the energies. This standard deviation was around 20%. And the worst case, some was down to 2%. Now I want to point out I took an 8 microsecond time step, and every microsecond I calculated the work for four samples here. Silicon carbide, monolithic plate, the 8090 4-row, the 8090 and a K5 encapsulation, and 995 in aluminum. And what to notice here is the silicon carbide plate after 3 microseconds outperforms all the other encapsulations up until 7.5 microseconds. At 7.5 microseconds, we see the unencapsulated ceramic spheres as well as the aluminum encapsulation outperform it. So that kind of points to we need a little bit more study done on the higher velocities and a longer time to look at it. So we should probably incorporate for future study a larger projectile on impacting so that we can have a longer tracking time. Presenting the areal density, all armor is measured in its areal density. One thing to note here is that the encapsulated ceramic spheres is far less than a monolithic plate. It's 2.83, where a monolithic silicon carbide plate is 4.14. So it's a significantly lighter plate. Here's the work performance versus areal density. What you're seeing here is the plates are in red, the 4-row non-encapsulations in green, and the blue is encapsulation, starting with HFM27 in these two, K5 in these two, and aluminum in this one. At 500 meters per second, we found that aluminum outperformed mass efficiency-wise at 500 meters per second, almost double. At 600 meters per second, though, you see the non-encapsulation and the aluminum neck and neck. And at 700 meters per second, the non-encapsulated 80-90% pure alumina outperforms all of them. And this matches our ballistic tests that we performed. The ballistic tests using the 30 caliber Mann barrel tests at 2750 at a minimum, they varied from 2800 to 2750 feet per second. The X5, which was the highly flexible encapsulation, you could kind of consider that as not encapsulated, performed rather well, only penetrating to 14 to 15 layers of the ultra-high molecular weight polyethylene, that hard pressed material that was passed around. But of note, the aluminum did outstanding at only 10 layers of the 35 heat pressed layers, pointing to this as an indication of its mass efficiency, that at higher velocities it performs extremely well. Also, the HFM27 and K5 performed pretty similarly, and that agrees with this performance here at a higher velocity. So our ballistic tests are in agreement with the gas gun. So in conclusion, the initial work was in the 8.2 microsecond region. We did various different targets and had great ballistic agreement. For the lower velocity shots, we noticed that the aluminum outperforms and the 995 variety outperforms all others in the mass efficiency. And for higher velocity shots, the unencapsulated has a higher mass efficiency. And on the basis of mass efficiency alone, encapsulation didn't really matter. And so for future study, recommendation is to enlarge the impacting projectile as well as increase its velocity. And additionally, compare this to hydrocode to something like CTH. That concludes my presentation. Any questions?